So today in my mind, I have some concepts to discuss. Those concepts are related to the week 2 sessions that you had seen lectures. Mostly, we will talk about the definitions, various circumstances, like when we have such situation, what to do, and there are various caveats that we need to be careful. Caveats are the means certain cautious situations. So, for example, in this case, first we will see the definition of limits that has been discussed by professor. So the definition of limits, the way is a mathematical way we can write this definition. For example, if there is a function f of x which is shown in a line, as you can see from a graph, and we just want to understand what do we mean by this particular equation which we have wrote here. What do we mean by mathematically? What does it mean? So basically we're going to write this whole expression in the terms of mathematics that I have shown here in green color. Okay, so you can also see this particular definition in a geometrical manner over here. On the x-axis you have the x variable, on the y-axis you have function fx. So here we see the variable x gets mapped to the f of x function because of this function, via this function, and we want to basically understand the behavior of the function when it takes a value x equal to a. We just want to understand this behavior here. So this definition of limits basically tells you how can we study this behavior. In the previous class I told you the meaning of limits in a English way, and also motivated you why we need limits. But in today's session I'll be more rigorous to the mathematics, and I'll see how can we write this mathematically by using the idea of neighborhood. In many textbooks you will see this kind of a notation, these notations are what called a neighborhood. So whenever we want to write mathematically a neighborhood around a point, so we use this kind of a notation in mathematical textbooks, where we characterize this neighborhood using this parameter. For example, delta, over here it's epsilon. So this particular notation is basically tells you the neighborhood around a point A which is related to this particular neighborhood which is on the x-axis. Okay, and this particular mathematical notation is related to the neighborhood around the limiting value. So this is all about the notations. Okay, so we say limit exists when the limiting value is equal to the value of the function at that particular point we want to investigate. In generally it might be equal to. So if f of a is not equal to L, when this is not equal to, when this equality doesn't hold, it doesn't mean that you cannot remove this, you cannot remove this discontinuity or such kind of a thing. You can basically remove them. You just have to redefine your function again at this point. For example, you might have a situation in which the value f of a was given here. So what was your curve basically? Your curve basically this black line earlier, and at this point, for example, if x equal to a, your function was defined here. So what I'll do, I'll redefine my function again such that I will manually assign that value was over here to here. The value which was over here defined, I will manually assign this to over here, and this is the way we can remove that discontinuity. So that kind of discontinuity we call as a removable discontinuity. But there are various instances where you cannot remove the discontinuity just because the left hand limit and the right hand limit are not same. Okay, so if the left hand limit and right hand limits are same, that means you have a limiting value, but that limiting value might not be equal to the value which is defined by someone. Like for example, I defined the function, okay, for example, which was over here, but I can redefine my function again and get that point over here. So this way I can remove the discontinuity. So this is all about continuity, discontinuity, and how can we remove the situations when you cannot. For example, like over here, for example, if we have this kind of a situation here, let's say the function was defined in this manner. You can see the left hand limit is different and the right hand limit is different. So in the first place your limiting value doesn't exist, so it doesn't matter how you define your function, this will not affect, this will not remove the discontinuity. Okay, so this is all about the discontinuity and all, but the main point was me to define this mathematically. So here what you see that for a given interval, so here I have wrote given word. Given means you fix your interval around your limiting value. Okay, you fix your limiting interval around your limiting value. This symbol represents such that, okay, this symbol represents such that there exist, this symbol represents exist, like exist, there will always exist an interval around the x-axis such that the distance, like this interval, like the distance between this f of x and the limiting value. F of x basically can be anywhere in the green portion. This is what f of x is. This f of x is basically what this, anything, any point inside this interval. And this modulus basically tells you the distance of the function with the limiting value. Here is your limiting value, and here all the f of x are. So what you are basically trying to calculate here is the distance between the f of x and the limiting value. And what we see that the distance between them is less than the interval which you chose earlier to start with. Okay, you can always find an interval around x-axis. You can always have an interval around x-axis. You can always find such that these distances are always less than the given interval which you gave to me. Let's say you come to me, like you came to me and you just gave me an interval around this limiting value. So I can always find interval around the x-axis, around that particular point which I am interested, such that all of this point will get mapped to this interval, all of this point. So that's what the meaning of the meaning of these limits, and this is how we write mathematically. Does anyone have any question like related to this green color mathematical thing which I have wrote? This symbol represents double implies. Double implies in the sense if you, yes, what question do you have? From which book is the practice set of problem uploaded? Those problem sets are from a university. They are not from any book. Those are from a university. They uploaded this problem set. Those are very simple problem set, just to give you the idea of like what they are. Yes, Amit, you have any question?
Sir, my question is that, yeah, am I audible, sir?
From it, just now I have just told you the meaning and some notations. Okay, so this notation means there exist. This notation means for all. Like I have written here in this yellow color, in this orange color.
That's fine, sir.
Tells you
That I understand.
all the values of x which satisfies this inequality satisfies this condition.
Okay, am I audible, right?
This expression, and these are the values. So geometrically means like all the values inside this interval in the x-axis. If you take a map with respect to the function, it will always get mapped to this.
Sir, my question is that, sir, we are calculate.
I mean, I cannot hear you.
Okay.
Are you speaking something? You can text if you feel like you can text me. Just give me the hint what exactly you want to ask. I might get the problem. Yeah.
Now am I audible, sir?
I want to make sure that you know this definition and understand this definition very well, because there will be questions. For example, they will just give you, like for example, limit x tends to 5 of given function equal to this, and you want to prove this using delta notations. These are known as epsilon delta notation of writing the limit. Okay, 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 I can understand. I cannot hear him. Like, can anyone text his question like exactly? I don't know why couldn't hear him. Hello, hello. Can you try again? Can you ask question again? Can anyone text his question?
Can anyone tell me how where will I get chat success?
See, now I can hear you. I can hear you. I can hear you. Can you ask questions? Now I can hear you. Amit, I can hear you. Please carry your question. Amit, I can hear you. So the picture which I have drawn here, the picture that I have drawn here, is basically tells you how the mapping is happening. Like over here I have drawn the x-axis, here I have drawn the y-axis. So what I'm basically trying to say that if you fix your interval around this limiting value, I can always find this interval. I can adjust this. It's in my hand. This is not in my hand because you have given me that interval, but I can adjust this interval. It's in my hand, and I can always find an interval such that all these points over here will get mapped inside this interval, but not all those points which are outside the interval.
Sir, we can't hear you.
Okay, okay, let me do something. Now you guys can hear me?
Yes, sir.
Okay, that's nice. So I'll repeat like what exactly I said. So over here you have this. I have drawn this particular illustration. Here basically I'm trying to show how we are getting those mapping. For example, over here we have drawn this x-axis, and here I have drawn y-axis. So the basically the definition tells you that if you give me any interval uh, which is around this limiting value, I can always find an interval on the x-axis which is in my hand. I can adjust this interval such that all the points inside this interval will fall or will get mapped with respect to this defined function inside the interval which you gave me. Any interval will won't do that. There is a critical interval. If I get that critical interval or shorter than that, I can always map those points inside this given interval which you give me, but not those points which are outside this interval. They won't get mapped. Okay. So this is what a simple graphical interpretation of what this particular mathematical notation tells you. It just basically tells you there is an interval around this limiting value. There is an interval around this x-axis which the with respect to the point which you wanted to understand the behavior of the function. And this basically this expression basically tells you you can calculate the distance between the function and the limit. So this basically tells you that those values which inside this interval and this limiting value, those distance will be always smaller than the interval which you give me. Now we can understand the importance of this small delta and small epsilon. We use them to represent a very small number, and we can, with using those epsilon delta, we can define neighborhoods. And this is the mathematical way we write those neighborhoods. So my question is where we are calculating value at in NBD of x, so neighborhood of x, the values we are getting is L, is limiting value. That value it tends to one exact value. Uh, yes, we yes, definitely we are calculating those values because we know them. Because the values of these green points are not the ambiguous point. You already know that. The problem is that you don't know this orange point. You don't have any information about that, and we want to understand what is the value at this point. So yes, we are basically calculating the values in the neighborhood, and using this value we are able to make comments on this particular value. So these are the what so this is what it means. You said, like, you can see your point can be seen over here. I hope this answers your question, right? So whenever I'm able to construct this definition, I would say yes, the limit exists. Limit exists. Okay. And if f of a is not equal to L, then we will redefine our function at f of x equal to a such that they will become equal. For example, you might have point over here but not here. So I'll just redefine my function over here. That's it. I hope this answers your question, right, Amit? Okay. Now I'll get to the important example. Over here we have function which is defined in such a way. It's basically multiplication of two functions. The first function is algebraic function and another is a trigonometric function. Okay, Harshit, you have a question? Yes, you can ask. So whatever you feel like, you can type. If you, I need to fix this problem because I'm unable to hear you guys. That's a serious issue. Hello? Hello? Yes? Yes, your question? Okay, so let me begin. I hope everybody can hear me, right? I did some changes in my audio setting. I need one thumbs up.
Sir, you are not audible, sir.
I'm not audible? Yeah, I can understand that. Am I audible now?
Yes, sir, now audible.
I think so, I'm audible now. Yeah. Just give me one thumbs up. Either my audio, either I can't hear you, or either my audio is not audible to you. So there is either situation. I have to fix this problem. From the next section, I'll fix this. So I won't be able to hear your voices. So please type. At least type some keyword. I'll understand your question. I'll help you. Just type some keyword. Okay. So the question. So the problem is over here. Basically, we have a function. Here we can see it's a multiplication of two functions. The first is the algebraic function. Second is a trigonometric function. And this trigonometric function is not an ordinary trigonometry. In the sense, the argument of this trigonometric function is 1 over x. And this plays an important role, this 1 over x. Whenever we have 1 over x inside this trigonometric function, they change behavior a lot. You can see the oscillations which you see becomes more tighter when you are closer to the center. For example, x equal to 0. Those oscillations are very tight. And you can see this algebraic function which is x, which creates an envelope, and inside this envelope you have this oscillation functions which oscillates. And why is it rapidly oscillating around x equal to 0? Just because of this argument, it's 1 over x. This makes this oscillation very fast around x equal to 0. And the more further you will go from the center, the oscillations will become less tighter. I hope this explains you why this function behaves like this. Okay, because you know the f of x is 1 over f of x. If you see the function very carefully, let me draw over here. If you see very carefully this f of x function, for example x equal to 0 to x equal to 1, you cover all your values from y equal to 1 to infinity. You cover all your values over here. So you can understand in this particular region, this value takes all values from 1 to infinity. And you understand the trigonometry function is a periodic function. It repeats its value. But the repetition is very fast because the argument of sine function changes very fast. Very fast. You can see from here. The value from y equal to 1, it goes to y equal to infinity in just by steps of 1. In the steps of 1, you can see the value changes like from 1 to infinity. You can understand like how fast this movement is. So this movement is responsible behind this tighter oscillations of this sine function around x equal to 0, and x and this algebraic function that we have multiplied to this sine creates an envelope. Okay, so this is how we draw functions whenever we have such kind of a situations. I hope this explains. Okay, so now how can we write this mathematically? We just want to understand whether this limit do exist or not. Here from graph I can see the limit exists. We can see the limit exists at the center. It's very trivial to see, right? Because your function converges to 0 at x equal to 0. So graphically I can see very easily the limit exists. But how can we see algebraically? How can we see in the terms of epsilon delta notation? So the way we study that, we first provide you an interval around the x-axis. Okay. Thing is that, no sorry, whatever I said, I'm sorry. I'll repeat once again what I said. So first you need to provide me an interval, epsilon, right? As according to the rule, right? You give me an interval. So you provide me an interval. Then I'll find what will be my delta. Because the theorem tells you that if you give me an interval, epsilon, I can always find a delta interval around here such that this will happens. So what I'll do, this is the epsilon, this is the interval which you gave me. Now I will try to find what will be my delta by using this condition, right? Because I want to satisfy this condition. In order to make this satisfaction, I will get my delta value. Okay, so over here, if you see very carefully, this function, okay, so we will just use the above definition, which is basically tells you the distance between the function and the limiting value is less than the interval which you gave me for a given interval around the x-axis. Okay, so we just use the above condition and we will calculate what is the answer. So we know that the limiting value is 0. So we will put the limiting value over here and we will do the calculation. We will end up with this modulus of x times of oscillatory function. But we know that sine function, we know very well that this sine function is always bounded from 1 to minus 1, right? Sine function cannot have values more than 1. Sine function cannot have values less than minus 1. Okay, and if I take a modulus, modulus means basically the distance from the origin, right? This is what the modulus means. Then what we see, that sine function is either equal to 1 or less than 1, the modulus of the sine function. So I can claim that this is actually less than this, right? Right, because I can write this mod of x times mod of sine, and this thing and this particular factor is actually a fraction, right? It's some fraction number, some fraction. So I can happily write this function as this particular whole expression as less than equal to delta x. So what I found that this particular whole definition is less than this. Okay, but I want to make this to happen. I want this distance to be less than delta, right? This means this delta of x should also be less than epsilon, and this is what the main key is, right? Because this is what it is written here. That means I can choose my delta equal to epsilon such that this will happen, right? Because this is what this definition tells you. So this is how we mathematically write to say limit exists and the limiting value is 0. Okay, I hope this idea is clear, right? Anyone, any doubt? Because I want to make sure this is correct, because in final exams you will be having a question like this where you will be given such kind of function and they will ask you limit exists and the answer is 0. Please write down in the terms of delta epsilon notation. These are known as delta epsilon notation. That means in the terms of intervals. That's another way, right? Any thumbs up? I hope the concept is clear, right? So this is what discussed in the class in the week 2. Okay, thank you. So the next concept which I want to discuss is, what if the limiting value is infinity, not a finite value? In this case we know it's a finite value, right? In this case we know what is L. L is a finite number. But what if this is not a finite number? I cannot write down a number. I have no other option to use infinities. Okay, so the way I mean to say that this is what happens. It's either plus infinity or minus infinity. But the idea is that the limit exists, but it's a very large number. So it's a very large number. So I don't know what is the issue in this. But I want to make a comment here. So whenever we have this situation, we always say limit don't exist. Because you cannot down, because the delta epsilon notation fails here. The problem is the delta epsilon notation fails here, because if you give me any interval, the problem is that you cannot define an interval properly here. It's very hard to define an interval around the limiting value, because you don't know this limiting value itself. So how can you define an interval around it? So the reason why when you have a L which goes to infinity, we say the limit don't exist, just because you cannot write this interval. You cannot provide me an interval. The problem is that. So this notation fails. So you need to keep in mind that whenever we have such situations, we say limit don't exist. Even though left hand limit goes to, for example, the right hand limit in this case, for example, this particular situation where you have this hyperbolic function. This is a classic example of rectangular hyperbola. If you don't know, you will come to know in future classes. So it's basically f of x equal to 1 over x, and I just want to understand what is the behavior at x equal to 0. And what I see that the left hand limit is plus infinity. It's a positive large quantity that you can see from this blue color, right? And the right hand limit, which is this, oh sorry, I'm just messed up the notation here. Okay, sorry for that. Let me fix this. This is minus infinity, this is plus infinity. Okay, so you can see the left hand limit plus infinity and the right hand limit is minus infinity. You can see from here itself. So first of all, the left hand limit and right hand limit are not same. So because of this, we can say limit don't exist. And also we say limit don't exist because those limiting values are not finite. Even if though they were same, for example in this case, instead of x we will use x square. Okay, so what happens, this will get flipped. Oh, I have made a wrong graph I guess here. Yeah, this is minus. Okay, so yeah, just bear with me little. So let's say if you square this function, so what you will get this kind of a graph, and here what you see that the left hand limit goes to plus infinity and the right hand limit goes to plus infinity. both the limits goes to infinity, but we still say limit don't exist. Okay, we just say the limiting value is very large number, it's a very large quantity. And the reason we don't say, because we cannot just write down a number, you know, we cannot define those interval things over there. But there is a way you can write mathematically this notation in a beautiful manner. You say that for any interval, in this case we are not defining an interval. In this case we are choosing a large number, you know, to characterize this value. See, we want to characterize this, we want to write down this infinite in a proper mathematical words. See, this is a graphical word, this is a graphical representation, but I want to write this algebraically because I want to use this information in some algebraic calculations. So instead of deriving an interval, instead of writing an interval, defining an interval over here, we basically say that we have a very large number. Let's say over here we have a large number. Okay, so we define a large number. No, it's a large number such that I can always find an interval over here. I can always find an interval such that the function will be more. The function will always be greater than that large number which you give me. Instead of defining an interval, we choose number. So I can always find an interval around the x-axis such that the values of the function will always be greater than the number which you chose or which we taken from somewhere, I don't know. And this inequality is satisfied by all the values inside the interval. Okay, so let me show you my own way of thinking. My own way of thinking is that you have basically two lines here. This line represents your x-axis, this line represents your y-axis. And I said that instead of defining an interval, we define a large m. I can always find an interval around the x-axis. I can always find an interval around the x-axis such that all the values inside this interval will get mapped to this blue lines. Okay, I hope the idea is clear. Any thumbs up? Any questions so far? Because this is how we write this definition mathematically. You might be having maybe 2 marks question or 3 marks question. For example, they will just tell you this is your mathematical, this is your limits, and tell me how do we write in this language. Okay, I can give you one more way of understanding what is the idea behind this. We'll take this discussion. In this case, I can see that. Let me use as many colors as I could. Okay, this is 0, right? X equal to 0, and this is some infinity, it goes like. So what this basically tells you that I can define an interval. Let's say this is x equal to minus delta plus delta. So you can see at x equal to minus delta there is a value, right? And the large m which I define to be this, right? For example, this is my large m. So what this definition tells you that I can always create an interval. You can see I can always create an interval such that inside this interval, let me use blue color. Inside this interval, if I map this, you can see all these blue points are greater than the m, right? You can see this, all these points which is get mapped because of these points. These are the neighborhood points which I defined, right? I can always find this interval such that the mapping, these blue lines, you can say the values of these blue lines is greater than the m value which you initially gave me. So this is the idea behind writing this kind of an expression here. So basically whatever I have told you, we have just wrote it in some symbolic way. This means for all, doesn't matter whatever the m you give, it works for all. So how is this different from the limit definition itself? They are same. They are same. The problem is that we don't know how to define interval at infinities. So instead of defining intervals at infinity, we define large numbers. Okay. So that's the problem. They are same, exactly same, no difference. Over here, if you see very carefully, the only difference is that over here we don't know the limiting value, right? In this case, let me write down here the difference which you have talked. That's actually a very nice question we have asked. The difference is over here. Earlier we had this kind of a situation, right? So earlier what we had this situation, but in this case you can see this goes to infinity, right? We don't have this part, but this limit goes to infinity, right? That's what I have drawn here. If you take any values inside this interval, those values, if you put inside this function, the value which you get from this function will always be greater than m value. So here we are not defining an interval, we are comparing the values of fx in this interval, the values of this interval. If I take these values and if I put it in the function, and if I compare the values of that fx with respect to this m, those values will always be greater than m. So that's the only difference. Earlier we told that this interval will get mapped to another interval, but in this case we don't know how to write intervals. The idea of interval fails here. So the only idea we have is to compare. See, we can easily compare, right? I don't know how to write this in an interval way, but for sure I can see these blue lines, the values over here is more than this m. I hope this answers your question. Okay. Any other question? Please feel free to ask, because in exams concepts will only help you, no matter how many questions you do. If you don't understand, that's a problem. Okay, we'll begin. So I can give you one good example. So example, what if x goes to infinity? We first saw what happens when the limiting value goes to infinity. But now we want to answer what happens if you want to study the behavior of a function when x goes to infinity. You want to understand the behavior of the function when I put a very large number inside the function. I want to understand what if I substitute x a very large number. What happens? You might have a situation, right? You might have a machine and you want to understand whether this machine can tolerate a very large number. You just want to understand. So thus the behavior of the function at a very large input is finite, infinite. You want to understand. So one of the ways we can write that particular situation is like here. So this basically tells you that limit x tends to infinity. That means we want to understand the behavior of the function for a large input value. And let's say some values comes, I don't know, some L. And I just want to understand. This might be finite, infinite, we'll see. We also might have situation in which we have this case to be infinite. For example, polynomials, right? Any polynomial you take, and if you put infinite values inside the polynomial, this will either give you plus infinity or minus infinity. How do I say that? Just because of graph, right? You check out any graph of polynomial. For example, straight line. See, it's minus infinity here, minus infinity here, plus infinity here. Parabola, again you can see both goes to plus infinity. If you take a cubic graph, some like random any polynomial, so the values for the larger values, if you put a very large value inside a polynomial, you will get output as a very large value. So this is a typical example. But you might not have polynomial every time, right? You might have an exponential function. For example, Exponential functions are heavily used whenever you have such kind of a situation. Okay, because there are lots of natural processes in nature. They do follow exponential laws. They don't follow polynomial laws. For example, how the decay happens. There are many nuclear properties happen in the exponential behavior. They follow exponential laws. There are various probability distributions. They do follow some kind of exponential behavior. For example, a population problem, lots of microbiological problems. If you want to calculate the population of cell inside if you want to just calculate the cell growth problems, those are also involves this exponential function. You might have also heard something called as Poisson distribution. Uh, that is also a function, a probability function. You will also see this kind of you will also see the presence of this exponential. So exponential functions are very important. Like as far as uh, you want to understand and study the behavior of our natural sciences, natural behavior, exponential plays an important role. So what we see that if I consider f of x equal to e to the power minus x, and I just want to understand what happens when x goes to infinity, you can see over here, this is where I'm talking about. So first thing you need to understand that just by looking the graph you can claim the answer. Just by looking the graph I can say the limiting values goes to 0, right? You can see this makes an asymptote to x-axis. Hopefully you guys understand what is asymptote. Asymptote basically tells you that limiting value, basically limiting behavior in the sense if I try to get a plot of f of minus x, this particular function at x equal to infinity, what I see is basically this flat line. That's it, right? I just see this flat line. This is what we mean by asymptotic behavior. Asymptotic behavior means the behavior at x equal to infinity, something. If you want to understand in a very simple English, even though which I am going to say is absolutely wrong, you shouldn't use those words anywhere. Just for your sake of understanding, you can see that asymptotes are basically where it makes a tangent and infinity. You can see it's like it makes a tangent, right? It looks like it makes a tangent, but you don't use this word anywhere. Okay, this is just for your understanding. So this function takes value 0. It not takes value 0, it just approaches as close as 0, but it never exactly becomes 0. So this is what we call asymptotic behavior, asymptotic nature, you can say. It is never equal to that value, but it is very close. The more higher values of x you take, the more closer you will get to 0. Okay, so I want to make this definitions clear. You might be able to see some those words somewhere in exam as well. And let me get back to the this problem again. So we see that the limiting value of this function at x equals to infinity is 0, and I just want to write down in a mathematical fashion. For example, this same copy paste what we have did earlier. In earlier case, I didn't know how to write interval around this limiting value, right? In this case, I don't know how to define interval around x, around that thing, right? In this case, I don't know how to define this interval. Right? In previous case, I didn't know how to define this interval, but now I don't know how to define this interval. The same exact strategy we're going to implement as what we did earlier. We will look for a large number. Instead of defining an interval, we will look for a large number and we will see the behavior. Oh, I went too far, sorry. So you gave me an interval around this limiting value. So I can always find a large number. Earlier what I said, I can always find an interval. Like over here you can see. Right? But in this case I am saying, I can always find a large number. Such that, let me write down over here. I hope this color is visible to all, right? M, what I have wrote. Hopefully, this color is visible. If any color is not visible, let me know. Okay, this color is visible. So the idea is that whenever I can always find a large M, and that value, that M basically corresponds to this what I have wrote here. So if you take any value more than this m, any value, sorry, I mean to say any values of x, and if you substitute that in the function, you will always satisfy this. You can see for all, right, for all x greater than m. So what do you see? The distance between the function and the limiting value is small compared to the interval which you give, right? That means I mean to say that here I have wrote that particular statement that I have said in a graphical manner. Here you can see there is x-axis, y-axis. You defined an interval around the limiting value, okay, and the idea is that I can always find a large number, and if I take the values more than the large number, these values will get mapped inside this interval. Always, I can always find. But if I take values less than this will not get mapped inside this interval. I hope this is clear, right? So if you want to understand this in a very crude language, just in English, so over here I have wrote it in English. For every interval around L, I can fix, or I can find, I can find such that the value of the function is very close to that limiting value, very close to that limiting value, or you can say that it will fall inside that interval. So now we'll get to the theorem. Okay, I got a question here. So in this case, there are thick mapping to the y-axis in a very small interval. Yes, that's true. Here you can see thick mapping in the sense, yeah, you can see, the differences of density, I mean to say. If you see the density, I mean to say, yeah, the density is little spread. You can say that points are little spreaded. Even though that's very hard to see because it's a continuous line, okay? So, it's just like an idea. Don't take it very literal, okay? Just, it's an idea. We have this notion called as density of points in mathematics. You will learn them in higher classes. For example, when you go to the masters, when you go for this hardcore mathematics, over there we will define this densities kind of an ideas. So for the crude way you can understand this, the densities are different here. Yeah. Now the most important theorem is that I don't want to check my limit as if they are unique or not. It's better I use a theorem which already exists, because in mathematics you should know what to use and what not to use, when to verify, when not to verify. If already a work is done, it's better to use that. Okay, if someone showed you that if a limit exists, then that limit is always unique, it's better to use that, right? Why would I try to figure out each and every possible limits for each and every different question? If I prove a statement which carries a general structure, then I better use that structure in my problem, because my problem is a special case of this. So it's not bad to use someone else's work, but you should always cite their work, okay? So always write down this theorem, using this theorem, okay? So whenever you are using anything, just write down using this theorem, uniqueness theorem. If someone asks you what is this theorem, people say this is a uniqueness theorem. So in your question paper, in your answer sheet, if you want to say I have got a limit, and without proving that this limit is unique, you have to write down using the uniqueness theorem, limit is unique. So this theorem tells you if you find a limit, then that limit is unique, and here's a simple proof. And the proof tells you that okay, so we will begin with an idea, the idea of contradictions. So whenever in mathematics, for example in pure mathematics, when you have a particular statement to prove which has to do with uniqueness, or maybe a binary kind of answer, yes or no kind of thing, the idea of contradiction helps you a lot. Most of the problems are solved just by using idea of contradiction. You first assume that the counter statement is true. For example, in this case, the counter statement is that limit is not limit is not unique. For example, I have two different limits, two different limiting value. So this is what the first statement tells you, that they have a distinct limits. I will try to prove that counter statement, and if I fail to prove that counter statement, then I'll say my counter statement is wrong. Thus, my actual statement is correct. So that's the idea. So, what do I mean by when I'm failed to prove my counter statement? I say that I fail to prove my counter statement whenever I find contradictions. Contradictions in the sense, while writing my statement, I had some assumptions, but later in my proving, I found that my actual assumptions were broken, were wrong assumptions. And so this is how we say the counter statement which I started with is wrong statement, and this is how I say my counter statement is wrong, because earlier I had some assumptions, but later in my proof of lines I found that the assumption which I took earlier doesn't hold good. There is a wrong. Those are wrong assumptions. For example, over here the assumption is L is not equal to M in writing down this counter statement, but later when I go through steps, what I found, the opposite of the assumption which I got, right? So this statement basically tells you the assumption which I took earlier is wrong. Thus, my counter statement is wrong. Thus, my theorem, so my actual statement is correct. I hope this idea is clear, right? I was much more interested in the philosophy of the kind of proof in mathematics we do. Okay. So I can tell you the quick answers. First we write down the statement for the statement for first limiting value over here, for example L. Then we write down statement for the second limiting value. Okay. Then what we do, we smartly choose the smallest interval. Why the smallest? Why not the largest? Because the smallest interval will guarantee that both statement is correct, because I want both of the statement to be whole true, and the only way that can happen if I choose interval which is even smaller than this intervals, because that interval will make sure this hold true. If this is correct, because this is true, because this is true. I hope my idea is clear, right? Okay. So choosing an interval which is smaller than these values will make sure these two statements are correct. And in doing so, we started with this. We saw the distance between the L and N. Whenever you see such kind of things, you should always you have a picture in your mind, is that there is a distance. Okay, you have two numbers and you're trying to calculate its distance, and this is a fixed quantity, right? Because L and M were fixed, right, earlier, and we did this addition subtraction. You know what we say, I created something from nothing. Yeah, this is what we say in mathematics. We created something out of nothing and we did manipulation. Over here I have used something called as triangles inequality, and it has a triangles inequality is very important, because whenever I say word distance is only true when it follows triangles inequality. You might be wondering, why is this triangle inequality? How the triangle is doing here? What triangle is doing here? See, the idea is that I need to include a page here, I guess. Okay. So the idea is that, so let's say you have a triangle here. You know that this is sides A, B, C. Whenever I add any two sides, and that value will always be greater than the third side. This is a property of triangle, right? So why am I saying this? Because I am telling you that this ABC has to do with distance. If anything has to do with the distance, it has to follow this kind of a property. Okay, so I'm telling you that this is distance, right? This tells you the distance between x and y, right? So I can always have a figure. For example, here let's say I have a 3 points x, y, z. So what is the distance between x and y? That will be this. So what is the distance between y and z? Y minus z, and distance between the x and z is this. So since this is correct, this is our old good school mathematics, right? But the same thing carry forwards to our higher education as well. Okay, the idea is that instead of just writing ABC, I'm using modulus, this mod, which is a more proper definition. I would say more precise way of writing things. So what I see here is that mod of x y plus mod of y z is greater than. You can you can you can choose any combination you feel. It's true for all combinations. Okay. So this is what we say a triangle's inequality. Okay. So over here we use that triangle inequality. I hope everybody knows this triangle inequality business, right? We can see where we have A, where we have B, and we have splitted that. So you need to be very careful. So let me write down those who don't know this particular fact. So let's say we have two quantities inside this modulus function. So we can always write this as this. So this particular left hand side is always less than equal to the individual sum of the modulus. Individual modulus sum. And hopefully many of you know this, that this particular quantity is greater than equal to the difference between the modulus. See, again, distance of distance, right? Let's say this corresponds to, if anyone has any confusion, let me write down. Let's say mod A corresponds to, for example, L1, some distance D1. Let me write D1 to avoid confusion. The mod B corresponds to distance D2. Then what I can say that, okay, so this will be equal to D1 plus D2, and this is basically D1 minus D2. So whenever you have, when you only matters, when distance only matters, when the difference matters, not the sign, we use this kind of notations over here. We use this kind of a notations. When difference matters, not the sign difference. There are two ways, right? Okay, so that's the idea. So here we have used triangles inequality, and since this definition is true, so I can write down this equal to epsilon, this equal to epsilon, right? I just borrowed this, I wrote this using these two statements. That's it, right? And one more thing I just want to clear, in case if you are wondering. For example, if A is less than B and B is less than C, I can happily write A is less than C. I hope nobody has any question in this. And this is the flow of logics. This is the flow of logic I'm using here in this case. That's it. Since this is less than epsilon, this is less than epsilon, so the addition should also be less than 2 epsilon, right? That's it. So the idea is that since you gave me an interval like this, you gave me an interval because this interval was given by you, right? And you can give me any interval. There is no restriction in that. The restriction is in the choice of delta. The restriction is in the choice of delta. There is no restriction over here. And the philosophy behind this intervals is that when you're doing experiments, the customer is happy with wrong answer, but not very bad answer. Customer do understand. Let's say I am doing an experiment. I know I can never get exact answer, but I want my answer as close as possible to the exact answer. So I need to get a cutoff, right? Okay, if I get an answer within this cutoff, I'll accept my answer. I'll accept this as my answer, because I can never get my real answer. I can never get my actual answer. So in the science field, in the engineering and the science, we say this as a confidence level. This is the confidence is in our answer. So whenever you present your results to someone, you just not say the answer. You say in this confidence. I have confidence in my answers, and you quantify that confidence by this way. So whenever someone says you 3 level of confidence, 4 level of confidence, so they mean by this. Okay. So let's say I'm trying to figure out what should be my experiments. How should I adjust my experiment? How should I adjust my experiment such that I get my answer within this confidence? So this is what physically this means. Probably you might have heard all these things mathematically, but since I work in physics, since I'm in physics background, so I'm much more interested in actual meanings of this mathematical statement. So this is what we mean experimentally. This is how we set up. So first we discuss among ourselves and try to fix our confidence level, and based on that confidence level we do all the analysis, and we determine this should be our experimental setup. That's it. I hope the idea is clear, right? Okay. So the next point we see here is that the next point over here, since proof is not complete yet, so this was the interval given to me, but in the calculations which I see that this particular quantity is less than 2 epsilon, but I know the epsilon given to me was this, and what I saw that the distance between L and M is less than distance between L and M. Basically what you are trying to say over here is that A is less than A. How can A be less than A, right? A cannot be less than A, right? So you can see over here, this is what you are trying to say, right? And don't get confused. These two quantities are same. I hope you're not getting confused like what I have wrote here. In case if you're not understanding, let me write this again. So this basically tells you that distance between L and M is less than 2 epsilon, but my 2 epsilon, my this particular quantity, if I substitute this over here, my 2 epsilon is basically distance between L and N. And what I found is kind of a funny situation, which clearly says that my old assumptions were wrong. So my actual conclusion is that no, L and M are same, because that's the only way you can satisfy everything, right? Because that's the only way out to your problem. So this is how you prove it, that L and M are same. Now we will go to my favorite example. Let me delete this page because this has nothing to do with. So my favorite example is this particular function, which we know as Dirichlet function, and this illustrates a very important property which we need to know. So can you kindly upload this notes despite uploading the tutorial to PDF? Yes, I will update. I will replace the original notes which is in the Google Drive with this current PDF. Okay, I'll replace it. I've not see. I might be having some additions over here. Yeah. Okay. Nice. You have got the message. Yeah. I'll replace the PDF. But that's the same notes that what you see in your Google Drive. You can simultaneously scroll that page if you wish. My goal is to present you that notes that I have created. Okay. So this function basically tells you that whenever you encounter a rational number, you give me an output as 1. whenever I give you irrational, you give me 1. Whenever I give you irrational number, I'll give you 0. And I want to make clear few points before proceeding, that rational number set is a countable set, but irrational number set is not a countable set. This first point should be clear. I hope everybody knows that. Thumbs up? Any? Yes, good. That must be very clear, because this seems to be a highly potential question in your papers. Okay, and the second point is that rational, if you see the size, if you see the cardinality is just basically the size of the set, nothing more. So if you see the cardinality of irrational numbers, that is more than the cardinality of rational numbers. This must be very clear. They have a different cardinality. That means you are more likely to find irrational numbers rather than rational numbers. Okay, you are more likely. So what you see, that the density of zeros are more than the densities of 1 as far as the output is concerned, and same way input is also. Okay, so you can easily see that this function is not at all continuous, not continuous each and every point, because the point just to your left is irrational number, the point just to your right is a rational number. LHS, RHS are never equal, no matter what point you take. I can always find a rational number and irrational number in any interval. That's the whole point over here, just to say that the limit don't exist. That's what written here. No matter what interval you create, because interval is basically a finite values, right? Basically this finite range, yeah, finite numbers, finite size, I don't know what to say that, infinitely countable set of numbers. Okay, so I can always find rational numbers and irrational numbers inside this interval, and the idea is that the limit exists when all these values map inside this interval, right? But they don't, because all your rational numbers, if I create a, let's say there is some limiting value L, right? And if I try to create an interval, I see that none of the values map to this, right? Because all the values either map to 0, either map to 1. Let's say your limiting value is 1. The problem is that I always have values inside this x such that they map to 0. That's the issue. So this function is a typical example where each and every point is discontinuous, where limit don't exist each and every point, and also since limit don't exist, they are not continuous, so they are also not differentiable. Okay. I want to make a comment. This kind of a behavior is also seen in stock market, because you see that the variations are discrete, they are never continuous. So you always see those points everywhere. But when you see the charts, when you say for example a chart of the any share price, you see they draw a continuous line. So why they are drawing continuous lines? Because everything is happening in a discrete manner, in a discrete fashion, right? I cannot sell more than compared to buy, right? Whenever we have a deal, the equal number of things being bought and equal number of things being shared, right? You never have a situation where the buying is more than the selling and selling is more than the buying. The idea is that someone is there to buy, right? So I mean to say, everything is happening in a discrete fashion as far as stock market or share is concerned, but still you see continuous lines. So what are those continuous lines? Those are average values. Okay, those are average values. Don't get confused to that. Okay, those are not the absolute values, those are average values. Now let's get back to the continuous function, because that's how I set up the idea of continuous. We just saw that this is a typical example in which it's not continuous each and every point. I'm planning to do a question before to begin with. I have a question here. to discuss. For example, here, over here we see a function which is the domain of the function is from -6 to 11, and the blue color is basically the definition of the function, or you can say this is how function is defined. And if you see very carefully, we have interesting points here. So the first question is, I just want to understand what is the limit. What is the limiting value of the function when x goes to -3? So basically trying to say here. So this question is to basically test whether can you see answers just by looking the graph. And just by looking the graph, I can easily see that the answer to this question is 0. Exactly 0. And the second question is tells you, let me mark it down here, 0, and I'll use different color now. What is the limiting value of the function when x goes to 2? And what we see here is basically trying to say here, right? And why did I say this? Because of this coordinate, right? Because this notation basically tells you x coordinate and y coordinate. So this tells you when x is 2, y is 4. Yes, exactly, the answer is 4. So the answer is 4, yes. And the next question which tells you the limiting value of function when x goes to 8. So here we have, yes, it's -2, exactly. So I hope you can do further questions. Now, but the interesting question is next. Is function continuous? Is function continuous in the given domain? What is the domain? Domain is this. This is your domain, right? Yes, the function is continuous in the given domain. Yes, there is no discontinuity, any ambiguity anywhere. One might argue, what about these points? For the boundary points, we only care about left hand limit and right hand limit. We don't care about left hand limit equal to the right hand limit, because we don't have definition of function here, right? We don't have any definition. In order to use those definitions, first we need to have values in that value. So the definition which you study over there, we exempt the boundary points. Okay, yeah, this exactly same. Now I have little more interesting problem like this. This is much more real situation, right? This is a very complicated function where you have ratios of two polynomial. Just by looking at the graph, I can say from my experience that these are ratios of two polynomials. Yes, they are discontinuous everywhere, not everywhere, to a certain points, but the idea is that those discontinuities, one of the discontinuity can be removed. For example, over here, if I redefine my function, instead of defining my function over here, I would better define this over here. By doing this redefinition, I remove this discontinuity. But I cannot remove this discontinuity at all, no matter how much redefinition I do. I can do redefinition for a single point, but not for this, right? You cannot do redefinition. This will basically change the whole function completely, because this captures an important property in nature. Can anyone give me example of this where you can see this? Okay, so can be or can't be removed means removable, not removable. So can be removed means you can remove that discontinuity by redefining the function at that point. Over here you cannot remove this, because when you're trying to redefinition, you're trying to make redefinition at this point, right? At x equal to 0. But no matter what value you give to x equal to 0, you cannot remove this discontinuity, right? No matter what you value give. But over here, in this x equal to 2, I can redefine my function by taking the value over here to here, and this will fix my continuity, right? But over here, no matter where I define, this will never fix my discontinuity problem. I will always have a situation where left hand limit and right hand limit are not same. So this is what I mean to say. Over here, discontinuity cannot be removed. Over here, the discontinuity can be removed. That's the key difference I mean to say. This is what I mean to say can removed, can't be removed. I hope this answers right. Amit? Okay. Uh, there is one more discontinuity over here. That's an interesting discontinuity. This discontinuity. This continuity can also be removed. But the problem is that while defining my function, I didn't give any blue point anywhere. This do not exist. Basically, the function was not defined at all. In this case, my function was defined. In this case, my function was defined over here. In this case, function is not defined at x equal to, let's say, -3, for example, over here. But still, I can remove the discontinuity by adding, okay, just by explicitly adding that number, yeah, because it is missing. Because x equal to -3 definition, x equal to -3 is missing in the domain. So I will add that. I will redefine my domain. Such that my domain union -3, and let's say the value is -2 here. So I will redefine my range as well. Union 2. So this will fix, right? I just have to add a dot here. My job is done. I have removed my discontinuity. That's an interesting, right? So this is what I mean to say over here. I hope this point is clear, right? Why is this removable discontinuity? Even though we don't have any definition in that part. Over here we had the definition, over here we didn't have any definition. In this case we had the definition, but we cannot do anything because I asked a question that where do we see this kind of a discontinuity in nature? Can you give any example? Like any example? I would be very surprised if you give me the answer. I just give you a title of genius. There are the technology is because we are interested in this kind of behavior in nature, because this is what we say miracle. This is what we see we have achieved. You might have heard this superconductivity everywhere, right? Have you all heard this superconductivity? Word superconductivity? Okay. No, okay. Let me give you more simple example. Have you heard of boiling of water, freezing of water, melting of water? Everyone heard this, right? So what are they? What is happening there? See, you know that water has three kind of phases, right? They have gaseous phase, they have liquid phase, they have solid phase. So what is happening at that melting point and freezing point? You see phase transition. You see that water converts from gas to liquid to solid. Some kind of phase transition is happening, right? So what do? You study those water. I will not tell you the names, but thing is that you try to plot some graph. So whenever you see this graph, this is a signature of phase transition. Whenever you see such graphs, you say there is a phase transition. So there are the signals of interesting physics that is happening. Let's say you might have a different mechanism altogether over here, a different mechanism over here. Yeah, might have. See, water behaves differently. Let's say this is liquid and this is your solid. Let's say when your water is solid, it behaves like this way. But when your water is liquid, it behaves as this way. So something has happened here, right? Something happened here. And you cannot have a liquid and solid together, right? So you always see a sharp discontinuities whenever you have the phase transitions. I hope the idea is clear what I'm trying to say. I just told you something very interesting. Something in real life we are very much interested. We look for such points. Yes, we also see that in stock market. But in stock market we do lots of renormalization such that we have a continuous graph. Yeah, that is also true. So this is what we see in real life, phase transitions. Whenever we have this kind of we look for this kind of discontinuities. We always look for these discontinuities. And one more fact I would like to, yes, yes, you have seen. Okay, okay. Hopefully this reminds you good old days of school, right? Hopefully this reminds you. I'm glad. So so whatever I have said in this graph, I would like to go one by one. I've written everything in this particular notes. Over here we see that x equal to minus 3 we have over here, for example, this. No, sorry, over here. So this is the point which we are trying to investigate. So it is discontinuous. So you can see this is discontinuous at this point, but the value is not defined in minus 3. So we saw two things. First, the function is discontinuous, and second, the value is not defined at minus 3. But we can remove this kind of discontinuity, right? This is removable, and I just said what to do. Just redefine. Just redefine my function at x equal to minus 3. Change your domain, change your range. Just add few points, and you are done with your job. Yes, can we say when we switch channels in TV, that type things happens? Yes, this happens. Yes, because channels have different frequencies, and those frequencies are not very close. Because if they were very close, then you would be able to see two channels at a time, right? For example, one of your channel works in different frequency. For example, to 398, for example, 398 megahertz. But your second channel, for example, works in 500 megahertz. And I want them to be far apart, and I want them to be farly different frequencies, because might be your machine is very sensitive to the neighborhood of this value, right? Though you set your value to be 398, but it doesn't matter, but it doesn't mean that your machine will detect only 398. It will detect some interval. We always have that kind of errors everywhere. You cannot just remove those errors. You will always have some, broadening errors. We call this as some kind of a broadening errors. You cannot remove this. So I want this value to be completely away from this particular error intervals. If that was not the case, I would be able to see both channels together. And I don't want that. So whenever you tweak your parameters and machines, you basically change, and you drastically go from here to here. So you always see some kind of, again, changes. So this kind of discontinuities are very important. They play a very important role in physics, nature, everywhere. In engineering, technology, you cannot just ignore them. Probably probably before this discussion, you might be thinking they are very headache. They are extremely headache, but I call them Nobel Prize. For example, to say they are important because they tells you that something interesting is happening. The physics which was earlier is not same. The physics have changed. The rules of game have changed. So this is what they say. The mechanism have changed. So basically, the superconductivity has to do with this kind of discrete jump. So superconductivity basically tells you that whenever, see, all the materials have some resistance, right? But there is a critical temperature. If you go below that particular temperature, your material will have zero resistance, absolutely zero resistance. This is what superconductivity is. And for example, I can show you. For example, this is your resistance and this is your temperature. So there is a critical value. We call that Tc. And let's say this is your graph. Let's say you're measuring your resistance of your substance. Let's say you're measuring resistance of your any object, and the value comes out to be this. But let's say you're lowering your temperature, so basically you're going in this direction, right? But the moment you hit a critical temperature, this value falls down to this value immediately falls down. So there is a sharp discontinuous, you can see here. Hopefully this explains the existence of this kind of a discontinuity in nature. They are much more. And what happens here, the physics, the game of rules, the game of physics in this range of temperature is very different compared to this. Over here we have something called as quantum mechanics. Here we have something called as classical. The classical is the same good old physics which you study currently. When you go to the masters and higher education, you will encounter something called as quantum mechanics, and this will explain you why do we have this kind of discontinuity. Because over here something else happens. The whole physics game of rules are different. So that's why we look for such kind of discontinuity in engineering and everywhere, to conclude our theory that there is something interesting happening which was not earlier. And this is how you write papers, your research papers. So currently what I'm doing, I'm looking for such discontinuities, but yet I haven't found one of them. And so I hope this point is clear, right? So what does this means? Now I'm looking for this case. This case is simple, right? So this case tells you it is discontinuous at this point, but the limit of left hand is not equal to the limit to the right hand, since there is a jump discontinuity. We call this a jump discontinuity, and you cannot remove those discontinuities. And at x equal to 2, we have something called as removable. I will not discuss again, everything is written here. But now I am very much interested in this kind of discontinuity. Let's say x equal to 6. Can anyone say what kind of discontinuity is this? Can anyone guess? I would be happy if someone able to answer this, because we see such kind of concepts in 11th, 12th as well. Yes, that's an infinite discontinuity. Yes, this is because the limiting value goes to infinity, and that's why we say limit don't exist. Hope you don't forget that message. And we cannot remove this discontinuity. We cannot remove this discontinuity. I have one more interesting point. I want to focus your attention at this values, at x equal to 5. What do you think? Is this continuous, discontinuous? What is this? Is this continuous? I can give you one hint. If you can draw a plot without lifting your pen, that's continuous. Yes, that's continuous. But there is something strange about this. This seems to be very jagged point, very sharp corner. And I hate sharp corners sometimes. Because what does this sharp corner signify you? This is to test whether you understand some concept called as differentiability, right? So let me tell you, this point is not differentiable. Yes, they are not differentiable. Because at left you have a different slope, and on the right you have a different slope, since the slope do not exist. So if you try to plot a graph of this, derivative of function with respect to f, what you see over here is an undefined value. Undefined. In the future classes, when we more precisely study this differentiation and all, what you see that your function is defined in this x equal to 5, but this might not be true for the case of derivatives. Derivative might not be defined in that particular values of x, so the domain get changed. So it doesn't matter, like there is a domain of a function, that domain is also same for the derivatives. Now derivatives for derivatives domain can be different, so you have to eliminate such kind of points here. So this is some basic idea. Okay, I hope this particular graph looks familiar to you now. Is there any discomfort with this graph? Anyone have any uncomfortability with this graph? I hope this explains your problem. Okay, I will begin to the next part. So in Rolle's theorem and LMVT, we see that, correct, that's true. Rolle's theorem and LMVT, yes, LMVT tells you Lagrangian mean value theorem, and Rolle's theorem is a special case of Lagrangian mean value theorem. So those who don't know, I'll tell you that you know what this things tells you, that the average slope the average slope is equal to to at least one of the instantaneous slope. I can give you a quick idea. What do I mean that? Let's say I have a graph, okay, and let's say I'm interested to this points, this and this points. So if someone asks me what is an average slope, so what I'll do, I'll just connect these 2 points, okay, and I will calculate the difference in the x value, which is delta x. I hope everybody can see here. And I'll just calculate the difference in the y. So I'll take the ratio, the delta y over delta x. This is what we call as average slope. Okay. So what this Lagrangian mean value theorem tells you, that this average slope is always equal to at least one of the instantaneous slopes. So if I try to get an idea, see, this is one of my instantaneous slope, right? Over here. It's basically one of the tangents, I mean to say. So the slope of this average, so the slope of this red line is always equal to at least one of the slope of the tangents, at least one. Okay, so that's the idea, and they are very important, because based on this Rolle's theorem and Lagrangian mean value theorem, I can make predictions what might have happened in between, right? For example, what I have discussed in the last tutorial session, I basically use Lagrangian mean value theorem to say that why this blue line is my answer, why not the other 2 lines are my answers. So I basically use the Lagrangian mean value theorem to explain you that. Okay, so these are the future discussions. So yeah. So now I want to tell you about some caveats. So caveats. So the idea is that first, the general method of calculating any limit is usually this 3 ways. You do substitution, the second is doing the factorization method, and second is the doing conjugate method. So these 3 are the different situations, and based on situation you have to implement one of the method. Okay, the first basic trial method is that you just go and substitute it, don't worry about. In this case, for example, you simply go and blindly substitute and hope that you get a finite value, and in this case we were lucky, we got a finite value. So once you get a finite value, pack your bags and leave, you are done with your work. But in the case of this, you might not get a finite value, because in this case you have something called as 0 by 0. Just by substituting you cannot get the answer, because you are getting 0 by 0. So you need to understand, like, from where am I getting this 0 by 0? I will cancel out that 0 by 0. I will cancel out those source of zeros. Because of those factors, you might be getting 0 by 0 form. And if you just cancel out that, you will get your finite answer. So the factorization method basically tells you there might be such factors, and because of such factors, those are redundant factors. So the moment you cancel them, you will get a finite answer. So we factorize this polynomial in such a way that we identify those sources of 0 and we cancel them, and we get a finite value. I hope this answers, right? I hope all are clear with this idea. This is very straightforward and simple. And the third method is conjugate method. You might have a situation like this: square root, some kind of a surds, SURD, surds. So in the case of surds, we do this kind of a conjugation, multiplication and division, because in this case you also have, again, you have a 0 by 0 form. So you need to figure out what is the factors, what are those factors which is creating a problem for you. But in this case it is not very obvious to do a factorization. So what we found that instead of doing factorization, we take the conjugate multiplication. So the moment we take the conjugate multiplication, surprisingly we see those factors and they get cancelled. So these are what called someone else effort, and you are trying to use someone else effort. This is an algorithm, you can say. You might have done in other ways, no issue in that, but this is the fastest way, proven and tested, and I would recommend you to do this. Recommend, but not the only. Okay, but I would be very much glad if someone might have asked me. I would be very happy. Like, you are not allowed to do this cancellation, because in mathematics we were taught that you cannot cancel 0 0. You cannot cancel, right? You cannot cancel zeros in your numerator and denominator. I hope everyone is getting this question, right? Why you cannot do this? This is, yeah, 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 exactly. That's the main difference between exactly equal to 0 and very close to equal to 0. See, these quantities are not exactly 0. These quantities are approximately 0. They are very close to 0, but they are not exactly 0. So the rule of not the rule that you cannot cancel zeros is true, but only for the exact values of 0, but not for the values which are very close to 0. You need to be very careful in that situations. So in this case we are able to cancel because they are not 0, they are close to zeros. That's the difference. And what if these three techniques fails? What if these three techniques fails? You are unable to do substitution, you are unable to do factorization, you don't know how to do conjugate method and all. Probably you might be ending up with such format, this 7 indeterminate forms. Probably you might be stuck with such kind of a forms in your problem. You might be facing this kind of a problem, which will not work, right? You might be stuck with this kind of a problem. And the note which I want to give you, the important note, I want to clarify that you can convert your problem from this form to other forms. You can convert. Let's say you are good in solving and dealing with problems of this kind of a form. Let's say you are good in dealing with this kind of a problem. Let's say I'm afraid of this kind of form. I'm very much uncomfortable with this, but I like solving problems in this kind of form. This is not told you anywhere. This is extra knowledge which I'm giving you, that you can always convert your problem from one form to another form. Always. There is a way. You can do this. I can give you one simple example. One quick simple example. Why am I saying that? Let me tell you this example. For example, sin x equal to x, sin x by x. This is a very simple example, right? And if I try to study limit x tend to 0, you will see that when you substitute, this actually turns out to be 0 by 0. And maybe I'm not comfortable with this kind of form, but I can change this problem into this kind of a form. I can change this to this, and the only difference I have to do that, instead of writing this way, I would prefer to write in this way. I hope you can understand. This becomes infinity by infinity. They are not 0 by 0 anymore. So everybody got this technique? You might be needing this technique somewhere, because probably. Okay, thank you, thank you. So this is the idea behind this. Probably you might be stuck with this kind of unknown form, and you don't know how to deal with this. So you can always convert this to this. So this is quite easy, right? That's the idea. So in principle, this kind of techniques exist. This is not a kind of surprising thing. So we have a mathematical hack, you can say hack. I will not give you the proof of this hack, but for the hack is that whenever you end up with such kind of a situation, this indeterminate form, you can always do this. Always. You can take a derivative of numerator and take a derivative of denominator, and you again try to get a limit of that of this particular quantity. Those limit will be same. So the original derivative and the limit of the derivatives of this numerator and denominator, those limits are same. So these are what called the L-Hospital rule, but it's actually pronounced as L'Hopital rule. Okay, it's L'Hopital rule where H is silent. So in this L'Hopital rule, you need to be you need to be careful of such cases. Okay, just be careful. This is like caveat. You can always do that. I can give you one example over here. For example, here. See, whatever things I'm telling you, it's always there in this Google Drive. There is a PDF of this problem sheet. I've just exactly copy pasted here. So I'm basically discussing that particular problem sheet here. So you see that here, whenever you have this indeterminate form, you can do this kind of a derivative in the numerator and denominator. I can solve this particular problem just by taking derivatives, and eventually hoping you will get your finite answer. See, this thing also works in this infinity by infinity. Just take derivative in the numerator and denominator, and you will end up with 0. I hope everybody understands the logarithm, right? Log function, right? I hope the knowledge of log function is clear to all here. Log is an interesting function. Whosoever is trying to go into the field of physics, anything related to information science, they better know this very well, log function, because that's the way we write down the information. Okay, so better they know this log function. They are crucial, I would say. They are crucial to this information science business. Actually, I received a question. So why we not concerned about the differentiability of f or g in the L'Hopital rule? See, thing is that no, it's not that we are not concerned. We are definitely concerned, but you will not face such kind of situation in your problem sheet. Let me tell you, there are much more rigorous mathematics is involved in this L'Hopital rule, and over here we take derivatives, and we don't want such kind of a situation. For example, some finite value over 0. We don't want this. So this is what basically tells you, those who have understood this particular statement which I discussed earlier. So this particular statement basically tells you, you better avoid this situation. Okay, you better avoid this. So this is where we need to be very careful about the derivatives, because we cannot do anything about this. This is completely undefined thing. End of discussion. For example, the example number 3, where we have this difference of infinities, and in this case you can see you have a finite value. Just not have a negative, you just not have some positive value. You might have a negative value, you might have positive value, and you can see just by substitution it just gives you this kind of form. And do some factorization, take derivatives. Yeah, that's it. You might have to do certain in between steps. For example, here they have did a factorization. They have take a factors. They have did some calculations in between. Oh, this is the interesting feature. 1 to the power infinity. You will encounter this a lot whenever you have exponentials in your problem. For example, in higher education, for example, when you try to do modeling of any theoretical science, any theoretical science, you will see such kind of irritating behaviors. So here you can see, if you put x equal to 1, you will see this kind of a form. So what we did here, we did manipulations before taking the derivatives, because you cannot define this, because here you cannot see fractions, right? You cannot see some f of x over g of x. You cannot see here. So we'll create that by taking logarithm on both sides. That's why I said you better know this knowledge of logarithm very well. For example, a to the power x. I don't see here some any kind of let me write down this way, some f of x to the power g of x. Don't see any fraction here, but by taking log on both sides, what do I see, that this becomes here and this becomes log of right, and then you can write this whole thing as log of f of x over 1 over g of x, and you will check whether this falls into 0 by 0 form or infinity by infinity form. That doesn't care, unless and until you have this numerator denominator form, you can apply your L'Hopital rule. So that's the thing which I want to discuss here, that you have to create that form. So it's exactly same thing what I have discussed here. Here you have created this into either this or that, and you use L'Hopital, because we know how to use L'Hopital rule for this and this. We don't know for, okay, you can do for this as well, there is no issue in that, you can do for that as well. I can tell you example, for example 0 into infinity. I can give you example like for example this x times of sine of I have to take this infinity, right? Yes. No, the problem is, let me write down some function. For now, just I'm interested in the idea. Let's say this function goes to 0, no, it goes to infinity, and this actually goes to 0. For example, x goes to 0. So what you can do, that you can redefine this whole function x over 1 over f of x, such that this becomes 0 by 0 form. That's it. You just take a reciprocal of that quantity, so you are able to make that particular fraction which you are interested in. So that was the whole idea I mean to say. So that's how we deal with this problem. X times e to the power minus x. No, that's not the true, because see, x times e to the power minus x, this actually goes to 1 when x goes to 0. This will go to 1 and this goes to 0. So when you try to take the limit, for example x goes to 0, this will go to 0. I'm trying to find a particular function which goes to infinity when x goes to 0. Maybe in future classes I'll come up with a function. So we know how to deal with this situation. We saw an example how to deal with this situation. We saw this by taking logarithms. Again over here also you can take logarithm. See, the moment you take logarithm of this form, this will convert to this, and the moment you take logarithm for this, it will get converted to this. That's it. And this will get converted to any one of them, depends on functions. Okay. Now we'll not discuss much. I will let you to go through this exercise, and if you have any question in the next class, you can just tell me the question number, maybe the example number which you don't find easy to solve. From then we can discuss that. And let me tell you few things before leaving. There are so many things I haven't covered so far, like actually this was the thing I was trying to say. We discussed this part is over. This part is done. So in this case, why limit don't exist, because you can always find numbers which maps to a two different point altogether. I was trying to discuss this continuous functions. So the only difference between the continuity definition and the continuous limit definition and the continuous function definition is that in this case, instead of L you put f of a. In the case of continuous function, your function is defined In the case of limits, the function was not defined. We don't know what is the answer. We were trying to estimate. And in this case, we know what is the answer. But the problem is here, not knowing the answer is not the issue. The issue is that, does this line is a continuous line or not? That's the issue. So completing textbook sum is taking forever. Yes, exactly. Completing textbook sum will take forever. But it helps to get a good grasp of the concept. Yes, exactly. Because the concepts are the only thing which will stay with you forever. Yes, concept stays with you forever. Question will help you to understand. Okay, so your major goal should be on the understanding. Yeah. Yeah. Today we will continue. We can continue in some next session. You guys can suggest me when. I'm up with any time. Like I will adjust my schedule in such a way that if you want to discuss in the next Monday, I can discuss on. We can discuss this on next Monday. Maybe if you guys want to discuss this in this particular weekend, someday, for example, Tuesday, Thursday, I don't know. Whenever you feel. I mean, I am unable to finish the portion. It's okay if you are unable to finish the portion, but try to get the idea as quickly as possible, because ideas can be written in a page. Ideas can be written in a page. So try to focus on the idea. Probably you will forget this delta epsilon notation, but try to understand what does this telling you, trying to say you. So we will do this. We will do by Thursday. First, it's possible. I can do this on Thursday. No issue. Since everybody know my Gmail, right? See, this is my Gmail. Mavish @ see, this is my email. So we can have a discussion, right, on email. So whenever you feel free, we can discuss. I think so. The time is up. If you have any suggestion, you can email me, right? Yeah. I'm one of the TA. I guess there is one more TA for this course. If I'm not wrong, there is one more TA. You might have to attend his session, right? He might be discussing questions. I'm not sure. Because the list which I saw, that for this course we have 2 TAs. It's me, and he's also one of my friend. He's in mathematics department from IIT Madras. I don't know who is answering the question in the discussion forum, because we have nothing to do with the discussion forum. But I'm happy to solve your questions. I have no issue in that. You can just email me. I will respond you with the answer. I don't know about this discussion forum. I have no access to this discussion forum. Probably this might be there is a different TA. I am assigned to clear your doubts, to do some tutorials, maybe how to solve questions, because my job is to make sure that you do well in your examinations. Basically support, I mean to say, where you can clear your doubts. Might be since you are watching videos, if I'm not wrong, in recorded videos you cannot ask questions, but in this session you can ask any question you wish. You are actually interacting with me. From next session I will fix this audio issue. Don't worry about this. I'll do something with this. I'll do something for this. Any suggestions so far? Let me tell you what I'll discuss in the next time. We will discuss some continuous function. We'll talk about some composition of function. I am sure, and I want to make sure that you do understand what do you mean by composition function. Book I recommend. There is one book known as, let me tell you the book. I study from this book. Yes, this book. When I started studying, I chose this book. My course instructor chose this book. I was in my undergrad, I guess third year. I had this course called as Real Analysis. Yeah, they are also very good books. This is the book which I started learning. I mean, uh, I'm not saying those books are also incredibly good. Um, but why am I suggesting that? Because these books contain everything, whatever you want for this course. It contains all questions. It contains all concepts. They also talk about all these intervals, definitions. They also talk about rigorous definitions. For example, I can tell you that, for example, this kind of a definitions. Like for example, what do you mean by interior points? What do you mean by compact set? What do you mean by closed and bounded? Those definitions are not very easy to understand in a single go. So, very careful attention is needed while understanding these concepts. There are various concepts because amazing questions can be framed using on these things. So here in this notes I have tried to make some diagrams to make you understand what do you mean by that. What do you mean by such statements? I mean to say, Thomas Calculus, definitely very good book for calculus, for questions related thing, I would say. Thomas Calculus is very popular for multivariable, not for single variable. The book which I showed you, this, I mean, they have questions, but these books focus more on understanding, modern understanding, I mean to say. That's it. I mean, do you have any other questions? I hope you understand my message, right? But I would say you can study from any book as long as you feel good, as long as you think you are getting better. There is one more book. This is called as I.A. Meron. Yeah, my professor, when he was studying, he studied from this book. This is a Soviet Russian book. It's the time of Soviet Russia. A very classic old textbook. It is available in English language, free of cost. I mean, the PDF is available. You just write the name, you'll get it. It's a classic Soviet Russian book. It's okay if you are unable to complete chapters in time, but what you can do, instead of focusing on details, very rigorous details, you better focus on the essence of the chapter, because the essence of the chapter is in a single page. You can write a whole essence in a single page. For example, what is the essence of a limit? In a single line, if I say the essence of a limit is to estimate, it estimates, right? So this is an essence of a limit. I have explained you what limits does without even telling you about epsilon, delta and everything. I hope this answers what I mean to say. Try to focus on essence, try to focus on message which this chapter is trying to give you. Try to focus on conclusions, some theorems, because theorems are the conclusion, I mean to say, the whole analysis. Because when you are done with your whole analysis, you write down as a point, as a statement, which we in Hindi we call as a patthar ki lakir. I have no idea of the exam patterns, because my job is to make sure you don't have any doubts. Complexities, I don't see the complexity would be tough, because as far as I know the professor, he's much more interested in understanding rather than making you to do mechanical business like this. He's not much interested in making you to do all this, because because the course was not defined to make you all this, make you to all do all this. The course is defined, the course is prepared in such a way that you understand such concepts which I'm discussing with you over here, which I'm going to discuss. So he will frame questions based on these ideas. If ideas are clear, no matter what they ask, you will be able to answer anything. See, these are answers. For example, bounded set. You will frame some question. For example, like graph, and then ask you what is supremum, what is infimum. Yeah. The questions will be straightforward. If you see those, I mean to say those, what we call assignments. The questions are straightforward questions. Uh, yes. See, sometimes we know concepts we can't write in mathematical way. So what your suggestion for that? Because mathematical language is, yes, definitely it's important when you're trying to make a career in it. If you want to make a career in the mathematical rigor, like the way it is done here, then you should know how to write down this. And the best way, I would suggest you to just shut up and calculate. That is what famously told by Richard Feynman. He's one of the renowned physicists. He said that for such situation, you better shut up and calculate. You better shut up and write. Just write and understand. I'm not joking. This was the actual word, and this is what our professors also say us. Whenever we go and ask such situation, he just says shut up and calculate. You will eventually get the hang of it, I mean to say. See, these are new language, new way of writing things, so this will take time, but I'm sure you will be able to write. I can understand your pain. I have gone through that particular stage. It's not easy, I can understand. I'm with you. Anything? I'm happy to answer any kind of question you feel. As far as the writing business is concerned, you better write. If you're not able to write somewhere, you get stuck, ask. But don't stop. Oh, thank you. So, we'll end up this session here. I hope this was helpful to all. Okay, see you on Thursday. Maybe, but I don't know how to contact with you. If I want to make a schedule for a class, I don't know how to contact. Any solution? Maybe I have to talk with my supervisors for that. Okay, if you guys don't get any update, right, then assume that you have a class on Monday. Okay, if there is an update you get, then we will do it on Thursday. Okay, if you receive any update, then that update would be on Thursday. If you don't receive any update, then we have it on Monday. Okay, hopefully you all guys got the email, right? So if you have any question, just ask me on email, no issue. Okay, see you guys.